The next problem we're going to work through is the rectangle area problem, which was number 6 in your optimization packet. We did this one along with the fence problem. So in this particular problem, we are creating a rectangle underneath a curve. So we're given a curve here, y equals 5e to the negative x, and we're looking only when x is greater than 0. So we're given the restricted domain. That's sort of nice. And we're asked to find the maximum area possible of this rectangle. Now, to give you a little bit of visualization of what's going on here, I've created this Desmos graph. So the red curve you see, that's the y equals 5e to the negative x, and this purple box that we see, that's the rectangle we're creating. And so we want to basically figure out where along this curve I'm going to get the biggest rectangle possible with the most area. So a good thing to notice is if I'm looking at this rectangle, its dimensions are basically described by where that point is on my function. So I'm going to go back to my work page and I'm going to draw myself a little sketch. So here's my coordinate plane, here's my curve, and I have a rectangle formed on the curve. And that point right there, we'll call that xy. And we know our curve is y equals 5e to the negative x. So when we deal with coordinate points, an x value is going to be our horizontal distance. So this length right here along our rectangle, that's going to be a length of x. And the vertical distance on a coordinate plane that we travel to an ordered pair is our y value. So we have an x and a y. So if I want to find the area of that rectangle, this sort of, that space in there, the area would just be x times y. Now, I have 3 variables. I don't want 3 variables. I want just area and one other variable. But we're given a function, y equals 5e to the negative x. So I'm going to actually take that particular function and use it to replace y. So I now can write area as a function of x. And I would have x times 5e to the negative x. So I've created a new function that would tell me the area of that shaded region, and it's only in terms of one variable x. Now we again want the maximum area, and maximums are going to occur where our function is either undefined or where our derivative is undefined, or where our derivative is equal to 0. So obviously I need a derivative. Now this derivative is going to be a little more challenging than our previous derivative because we have a product going on here. We have a product rule. And for those of you, just a little reminder, remember product rule. If I'm taking, the derivative of f times g, it would be the derivative of f times g plus f times the derivative of g. So I'm going to go back to my area function, so a prime of x. And you'll notice I sort of have built in here my 2 parts, sort of this one piece, the x, and then the 5e to the negative x. So the derivative of x is just 1. So I'd have 1 times 5e to the negative x. And then that's going to be plus x times the derivative of 5e to the negative x. Well, that is a little bit of chain rule because I have an inner function there with that negative x, and that derivative would be negative 1. So I'll have negative 5e to the negative x power. And I'm going to rewrite this to be a little cleaner. So 5e to the negative x minus 5x e to the negative x. And we're looking for where our derivative is either equal to 0 or undefined. That's going to be where our mins and maxes occur. Well, I have an exponential function, and I'm timesing it by a 5x. So there is actually no x values where this is undefined. But I can't, so I'm just going to be saying, all right, where's the derivative equal to 0? This particular function, you might be going, oh, I need to pull out my calculator. But it's actually less scary than you think. If you notice, we have a 5e to the negative x here, and we have a 5e to the negative x here. So I can actually factor that out, and I'd be left with 1 minus x. And now all of a sudden I have an equation that I could just solve by factoring. 5e to the negative x will never equal 0 because it's an exponential function. As our graph sort of showed, it's never going to equal 0. And 1 minus x is going to equal 0 when x equals 1. So I've actually found what the value of x would need to be. It would need to be 1. But let's go back to the original question. Always make sure we're answering what we need to be answering. We're asked to find the maximum area of the rectangle and state the dimensions of the rectangle and the maximum area. So I need to get my dimensions and my area. Well, to figure out my dimensions, basically y is equal, so let's change colors here. So we want to find our dimensions. Oops. Helps if I spell the word right. Dimensions. Okay, so we know that one of them is when x is 1, and so y is going to be equal to 5e to the negative 1 at that point, which I could think of as 5 over e, if that helps. And then if I want to find the area, remember, was just x times y. And so in this particular case, at these dimensions, that would be 1 times 5 over e, or 5 over e. So the rectangle with a max area inscribed under the curve y equals 5e to the negative x would have the dimensions of 1 unit by 5 over e units and an area of 5 over e units squared. And I don't have particular units because we're just on a coordinate plane. But again, my sentence sort of explains what I was asked to find, gives the dimensions, gives the area. And that would be how we tackle the rectangle area problem number 6 from your packet.